In the last video we saw that if a function is differentiable at a certain point, say z0, then the Cauchy Riemann equations hold at that point. We actually proved that fact. Now the converse is also true. If the Cauchy Riemann equations hold at a point, then the function is differentiable at that point. We didn't prove that. U and V are the real and imaginary parts of f of z. We will start this video by showing that the partial derivative of f with respect to x is the derivative of f with respect to z. To do that, we will write down f. The next thing we do is take differentials. To get du, we have to take the partial derivative of u with respect to x times the differential dx, and then we want the partial derivative of u with respect to y times dy. So for example, if x and y were, say, both functions of time and we were getting du dt, well, we'd have to use the chain rule. We'd first of all differentiate u with respect to x, then multiply that by the derivative of x with respect to time, then take the derivative of u with respect to y and multiply that by dy dt. So multiplying through by dt, you see that we have the differential du. And then we have to get dv. Well, we've I times dv, so we have to get the partial derivative of v with respect to x times dx, and then add on to it the partial derivative of v with respect to y times dy. Next, we apply the Cauchy Riemann equations. We use the fact that du dx is equal to dv dy. This is true if our function f is differentiable at some point xy. So we're getting these derivatives at the point xy. And since they're equal, we can factorize them out, so we can just write for dv dy du dx. So we can factorize du dx out of this, so we have dx left over here, and we have I times dy left over here. So that's the result of the factorization. The other Cauchy Riemann equation says that du dy is equal to minus dv dx, or dv dx is equal to minus du dy. So as a reminder, here are the two Cauchy Riemann equations. The first one's easy to remember. We differentiate u with respect to x, then we differentiate v with respect to y. U comes before v, x comes before y in the alphabet. And to get the second Cauchy Riemann equation, we interchange x and y in the denominators and change the sign of one of the derivatives. Okay, so we can factorize du dy out of both of these terms. So we'll get a dy, and because of the minus sign, we'll have a minus I dx. Now we want to get df dz. So we just divide everything by dz. Since z equals x plus iy, dz is equal to dx plus I times dy. X and y are the basic variables here. They're not functions of anything else. So they're both independent variables. So we're dividing by dx plus I dy. Now over here we see that the thing in brackets is actually I times the denominator. It's actually, sorry, minus I times the denominator. If we multiply minus I by the denominator, we get minus I dx minus I squared dy. Well, minus I squared dy is plus 1 dy. So we get minus I here. Now we can go back to using one of the Cauchy Riemann equations. That's this one here actually. We can replace minus du dy with dv dx. So we can replace this with dv dx. But this is just a derivative with respect to x of u plus vi, which is just a derivative of f with respect to x, since f is u plus vi. So that's this result here. We can also show that df dz is minus I times df dy. This time we replace du dx using a Cauchy Riemann equation. We can use this Cauchy Riemann equation here to replace du dx with the partial derivative of v with respect to y. We can write this like this here. We can factorize out I, and if you check this, you have I times du dy. Actually, it's minus I times du dy will give us this term here, and then we have minus I times the derivative of v times I. Well, the I is just a constant that can come out, so that gives us minus I squared times dv dy. But minus I squared is the same as plus 1. Since u plus vi is f, we get our result that df dz can also be written as minus I times the partial of f with respect to y. Let's take another example. We want to show that this function is analytic everywhere. That means it's differentiable everywhere. So we have to show that this function satisfies the Cauchy Riemann equations. So we need to find what u and v are by getting f of z. So z is given by x plus iy. We need to cube it out. So we cube the first term, x cubed. We've 3 times the first term by the second term squared. So that's 3x times iy times iy. Well, iy times iy is minus y squared. Then we have the the second term multiplied by 3 times the first term squared. So that's iy times 3x squared. That's this here, if we take out the I. And finally we have the second term cubed. That's I cubed, y cubed. Well, I cubed is I squared times I, or minus I. So now you see that the real part is u and the imaginary part is v. So we need to take partial derivatives of u and v with respect to x and y to see if our function satisfies the Cauchy Riemann equations. So let's get du dx. That's just 3x squared. We treat y as a constant, so we have minus 3y squared for this, the derivative of this term. To check the first Cauchy Riemann equation, we need to see that du dx equals dv dy. So we need to differentiate this with respect to y, treat x as a constant, and we get 3x squared for the first term and minus 3y squared for the second term. So there we have it. We see that du dx gives us the same result as dv dy. So that's the first Cauchy Riemann equation. Now we need to get du dy and dv dx. So we treat x as a constant here, and x cubed goes out, and we get minus 6xy here. We treat x as a constant. That's du dy. And when we differentiate v with respect to x, y cubed is just goes to 0, and we get 6xy. So you see here that du dy is minus dv dx. So the second Cauchy Riemann equation is true, and you can see that both Cauchy Riemann equations are true for all x and y, for all points in the plane. So that tells us that our function is analytic everywhere. We want the derivative of f with respect to z. Well, that's easy. That's just 3z squared. So the rules that apply for the derivatives of real valued functions also apply for the derivatives of complex valued functions. Let's look at the function f of z equals z bar, the conjugate of z. So we just change the sign of the imaginary part of z. So if z is x plus iy, z bar is x minus iy. We see that u is the real part x and v is the imaginary part minus y. If we get the partial derivative of u with respect to x, we get 1. The partial derivative of u with respect to y is 0. As for v, the partial derivative of v with respect to x is 0, and the partial derivative of v with respect to y is minus 1. We see that du dx is not equal to dv dy. 1 is never equal to minus 1 for all points in the plane. Du dy does equal minus dv dx. The second Cauchy Riemann equation is satisfied, but that's no good. The first one is not satisfied, so it means that the function z bar is not differentiable anywhere, not even at 0. Let's look at the function 1 over z. What are the real and imaginary parts of it? Well, this is 1 over x plus iy. Now we want to write this as a single complex number, so we multiply above and below by the conjugate of the denominator, which is x minus iy. In the denominator we have a complex number by its conjugate. That gives us the square of the modulus of the complex number, which is x squared plus y squared. So the real part is x over x squared plus y squared. That's our u. And this should be minus y over x squared plus y squared. Okay, let's get du dx. So we need to differentiate this first term with respect to x. We need to use the quotient rule here. So I take what's underneath, x squared plus y squared, times the derivative of what's on top with respect to x. That gives us 1. Then we minus what's on top, which is x, by the derivative of what's underneath with respect to x. That's 2x. And we divide the whole lot by the denominator squared. As for dv dy, we have the denominator x squared plus y squared times the derivative of what's on top with respect to y. That gives us minus 1. Plus what's on top, which is minus y, times the derivative of what's underneath with respect to y, which is 2y. And we divide the whole lot by the denominator squared. Now we can show that these two are equal to each other. Well, obviously the denominators are equal. As for the numerator, well, you see what you get. You've 1x squared minus 2x squared. That's minus 1x squared. And we have a plus y squared. Now, as for the numerator here, we actually have two minus signs here. I left out a minus sign. We take the denominator times the derivative of what's on top, minus what's on top, which is minus y, times the derivative of the denominator, which is 2y. So we're going to get minus 1 times x squared. Well, that's going to give us the minus x squared, same as for the previous derivative. And then we have minus y squared plus 2y squared. That's going to give us plus 1y squared. So we have a minus sign when we're differentiating a quotient. So the first Cauchy Riemann equation is satisfied. Du dx is indeed equal to dv dy. To get the second Cauchy Riemann equation, we just interchange x and y, and we minus one of the derivatives. So we get du dy equals minus dv dx. I won't bother running through this. It's just more quotient rule, and it turns out that it's true. So both Cauchy Riemann equations are true everywhere for all x and y, except when both x and y are 0, because then we have division by 0 here, so we can't even get the derivative. Actually, the function is not even defined at 0. If both x and y are 0, then obviously z is 0, so the function isn't even defined at 0. The derivative of f of z is minus 1 over z squared. So this is just like differentiating a real valued function. Say 1 over x is minus 1 over x squared. In this example we have the function z times z bar. That's x plus iy times x minus iy. So we're multiplying a complex number by its conjugate, and we know that that gives us the square of the modulus of the complex number. The cross terms cancel out, so we get just x squared plus y squared. No I appears. So the real part is x squared plus y squared. The imaginary part is 0, since a complex number times its conjugate always gives us a real number. Du dx is 2x. Dv dy is 0, because v is 0. So you can see straight away that du dx is not equal to dv dy, except when x is 0. If x is 0, we have du dx equals 0, and dv dy is 0. So the first Cauchy Riemann equation, du dx equals dv dy, is satisfied only when x is 0. Now the second Cauchy Riemann equation is got by getting du dy and dv dx. So if we differentiate u with respect to y, we get 2y. If we differentiate v with respect to x, we get 0. So the second one is only satisfied when y is 0, because then du dy equals minus dv dx, or 0 equals minus 0. So both Cauchy Riemann equations are only satisfied when both x and y are equal to 0. For a function to be analytic at a point, remember that the function has to be differentiable in a region containing that point. This function is only differentiable at a single point, z equals 0. So if we have any region, no matter how small, containing 0, the function will only be differentiable at one point. So the function is not analytic at 0. It would need to be differentiable at all points in the region containing 0 if it is to be analytic at z equals 0. So the function is not analytic at 0, and since the function is not differentiable at any other point in the plane, the function is not analytic anywhere.